Hello everyone, and this is the second part of our lecture 5. We're finishing section 1.5. So here, guys, I'm going to introduce you with a set of equivalent statements, which is going to be one theorem, consisting out of several theorems. So what are those equivalent statements? If you have A and N square matrix with dimensions n by n, then next four statements A, B, C, and D are going to be equivalent. Means that either they are going to be all four true or all four false. Which means that if statement A, for example, false, all other B, C, and D are going to be false. If statement A is true, then B, C, and D are going to be true. How I'm going to prove this theorem? Well, first let's read it. So next four statements are equivalent. Matrix A is invertible. Equation AX equals 0, homogeneous equation, has only trivial solution, means that the only solution is column of X equals 0. Reduced row echelon of matrix A is identity matrix. And the last one, matrix A, is expressible as a product of elementary matrices. I'm going to do the proof in order, I'm going to start with C, D, and then I'm going to move to A, B, and back to C. So I'm kind of going to be something like this. C, D, then D, A, then A, B, and then B, C. Kind of weird way of doing this. Why? This is my choice. Well, guys, let's look at statement C. Reduced row echelon form of A and N is identity matrix. We already had this theorem, the proof from C to D just before, right? If reduced form, I'm going to kind of show that, let's C to D. If reduced row echelon form of A is IN, means that we can express it as a product of elementary matrices. Then A can be expressed as a product. We just proved this theorem, and they are going to be what? Inverses of like A inverse one. Oh, sorry. Let me write it down one more time. A one inverse, A two inverse, and eventually E K inverse, right? Well, we just proved this, so I'm not planning to prove it a second time. We just know that if you can bring by row operations A to identity matrix, then you can apply, like, you can write down that A as a product of inverses of this. Well, in our proof, actually, we had this identity, right? Well, you probably still remember the proof. I was just kind of doing this, like operations and then multiplied by inverses. So that's the first part. It's expressible as a product, right? Now, the second part is from D goes to A. We also proved this already. If A is expressible, if A can be represented like this, then we can use it to find A inverse. Remember, kind of, I'll just want to remind you that, uh, that A uh, uh, by A inverse equals identity, right? And instead of A, we can use this form and then multiply again by uh, direct matrices, and we are going to have I and E1, E2, and EK, and that's going to be A inverse, right? A inverse is going to be the product of like elementary matrices which correspond to elementary operations. Well, basically we proved it already. Like in the first part, I don't want to prove it again. So the matrix is invertible. We just kind of can show inverse. And because we do know that inverse is, that's going to be inverse, right? Now we're going to prove uh, statement A to B. So imagine that A is statement A to B means that A is invertible. We're proving that it's going to have only trivial solution if A has A inverse. Then what can we do with equation? Imagine that we have equation AX equals 0, homogeneous equation, with that matrix of coefficients. Let's apply inverse to this equation. Let's multiply it by inverse. We do know that inverse exists because that theorem states it's invertible. Sorry, A inverse by A by X, and on this side is going to be A inverse by 0. We do know that A by inverse is identity, right? And we do know that any matrix by a 0 column is going to give us 0. So what is identity multiplied by X? Well, that's just X. And what does it mean? That's just a trivial solution. Trivial solution, right? So trivial solution is solution which consists out of all zeros for homogeneous system. So we kind of proved this one, right? That it has only trivial solution. All x's are equal to 0. Remind you, x1 equals 0, x2 equals 0, the only solution of the system. So last step we have to do is to prove that from B follows C, right? To kind of finish our circle. So we prove this, we also prove this. The last one, we are doing B followed by C. Okay, so what B tells us? B tells us that the equation has only trivial solution, right? So AX equals 0 has only trivial solution. Well, trivial solution means that x1 equals 0, x2 equals 0, xn equals 0. Guys, why do I write down this axis not to zeros, but like in a diagonal? Because I'm trying to imagine that, okay, when x1 equals 0, x2 equals 0, it's going to look for me as a product of I x equals 0, right? Just like if you imagine that identity matrix, what is identity matrix? It consists out of all ones. Well, what does it mean? It means that, like, if you take matrix A and start doing like Gauss-Jordan elimination on it, Gauss-Jordan elimination, and you kind of get the first coefficient equals to 1, and all like others are zeros, and all others are zeros. It's going to mean that we don't have this row of zeros. Because if we do have row of zeros, we are going to have arbitrary solution. Like imagine that the last row is row of zeros, means that xn multiplied by 0 equals 0, and xn can be anything. But we don't have this. We have only trivial solutions. So, which means that all coefficients in our reduced row echelon form are sitting on diagonal, and they are identity matrices. So that's basically a proof. So actually, this is like identity matrix. Because like if you like imagine that, what is the solution? Solution is going to have only like coefficients, one here, one here, one here, and all zeros in front of others. And which means that we have like 1, 0, 0. That's reduced row echelon form, right? Because usually by Gaussian elimination, we get this reduced row echelon form, and that's going to be reduced row echelon form, which consists out of ones here on the main diagonal multiplied by corresponding variables and zeros everywhere else. And this is kind of identity row echelon form. Well, which means that, yes, yeah, we proved the last statement. that reduced row echelon form is identity matrix. And again, remember, there are two options for reduced row echelon form, to be either identity or to have a row of zeros. If we do have row of zeros, again, it's not going to be only trivial solution. It's going to be like more solutions, like let's say infinitely many, because homogeneous equation can have either a trivial solution or infinitely many solutions. Okay, well, hopefully, guys, you will remember this theorem. I'm not going to ask you to prove this theorem, but I want you to remember the theorem that these four statements are equivalent. So matrix is invertible, has equation has only trivial solution, which is not like that easy come with invertible, right? And the reduced row echelon form is identity, which is more related to trivial solution, right? And A is expressible as a product of elementary matrices. Doesn't look like any clues in previous three to bring you to this conclusion. But all these four very, very unrelated on the first side statements are actually equivalent to each other if you are talking about matrix A. Okay, we're gonna remember these statements and eventually maybe use them, but I think that's all for now. And thank you. That was the end of section 5 and our lecture 5 too.